All right, so in the last part of section 1.1, our previous video, we talked about what it means for a differential equation to be linear or nonlinear. And now we're going to move on to the discussion of solutions to a differential equation. So what I'm going to be using to represent kind of a general nth order differential equation is this. F of x, y, y prime, y double prime, y triple prime, so on and so forth, all the way through the nth derivative of y equals 0. Any nth order differential equation can be represented this way, and it's just kind of helpful to have a very general way of representing a differential equation. So that's what we're looking at. This is just, think of this as just any differential equation, an nth order. So an n times differentiable function defined on an interval I is called a solution to the differential equation shown here if that equation reduces to an identity when it's substituted into this. Now, all that really means is a function is a solution to this differential equation if it satisfies this differential equation. In other words, if I plug it in and if I take all of the derivatives that I need that show up in that differential equation, plug all of those in, this equation becomes an identity. It's something that's true. So to give you an example, let's take a look at a differential equation, this one shown here, y prime plus 4xy equals 8x cubed. Notice the y is the thing that we're taking the derivative of, which means x would be our independent variable here. And I'm giving two functions that I'm saying are solutions to this equation. I would like to check both of them to see that they are in fact solutions. So here's the simpler one. We're going to start by looking at y equals 2x squared minus 1. How do we verify that this function is a solution to this differential equation? Well, what we need to do is plug it in a sense. But in this differential equation, not only is y showing up, we also have a y prime. So if this is y, I'm going to need y prime before I can verify that this thing is a solution. So what is y prime? Well, y prime in this case is just 4x, took the derivative. Now, I want to take this differential equation and substitute the y and the y prime in wherever they are supposed to go. So I have y prime, which in this case is 4x plus 4x times y, which in our case is 2x squared minus 1. Okay? Now, if I plug that in and simplify, or if I distribute the 4x and simplify, I get 4x plus 4x times 2x squared, or 8x cubed, minus 4x. And the 4x and the minus 4x would then cancel each other out and give me just 8x cubed. Notice I get 8x cubed, which is what the right-hand side of this differential equation looks like. So using that substitution, I'm getting what I'm supposed to be getting. Let's verify that other function that we're saying is a solution. If I suggest that y equals 2x cubed minus 1 plus e to the negative 2x squared is a solution to that dE there, then I should again find y prime first and try substituting things in. What is y prime? Sorry, not 2x cubed, 2x squared is what I have written here. So again, this would be 4x. That goes to 0, and then the derivative here is going to be minus 4x e to the negative 2x squared. Okay? And then we're going to substitute this in to our differential equation, see if it comes out true. So y prime comes first. That's 4x minus 4x e to the negative 2x squared plus 4xy. Plus 4xy in this case looks like this. 2x squared minus 1 plus e to the negative 2x squared. Distribute that 4x in, I get 4x minus 4x e to the negative 2x squared plus, so let's see, this will become 8x cubed minus 4x here plus 4x times e to the negative 2x squared. I see cancellation here and here, as well as here and here, and I'm left with that 8x cubed, which is the thing I was hoping to get, because that's what's going to establish the right-hand side of this equation. So these are two different solutions to the same differential equation, and they're different. They have some similarities. They both have a 2x squared minus 1 in them, but this one has an entire term that this one doesn't have. And so that does kind of raise the question, how many solutions are we going to expect from for a differential equation? And we'll look at that in a moment. One other thing I want to mention here too, and we're going to look at this in more depth also, is that a function that's acting as a solution to a differential equation is always defined on some interval. Now, the solutions that we got here are defined on the entire real line. The domain for both of these functions is all real numbers. And so the interval in this case that is acting as our domain for this solution is just the open interval from negative infinity to positive infinity. But we have to take some special care in certain cases in dealing with that interval. So we're going to talk about that next. The interval that I'm talking about for a solution to a differential equation, we oftentimes call the interval of definition. It goes by other names as well. Interval of validity is a common one as well. And we're going to kind of investigate this in a minute. One other term that's going to be important, that's going to come up again and again throughout the course, is trivial solution. If a differential equation has the constant function y equals 0 as one of its solutions, we refer to that as the trivial solution. So this specific solution is called the trivial solution. All right, now that that's out of the way, I want to talk a little bit about the difference between a function just in its own right as opposed to a function being a solution to a differential equation. So first of all, when we have a solution, like the two solutions that we just checked for that previous example, a solution to a differential equation, we refer to its graph as a solution curve. Now, in some cases, this was not the case for the example that we just did, but in some cases, the solution that you get for a differential equation is a function that has discontinuities in it of various different types. It could be asymptotes, it could be jump discontinuities, it could be anything, but they may not be continuous everywhere, they may not be defined everywhere. And in those cases, we have to be careful. So let me show you an example here. Here's a differential equation, xy prime equals negative 2y. A solution to this, one solution to this, is the function y equals 1 over x squared. Now, I'm not going to verify that, but in light of the previous example, you now know how to verify that this is a solution to this. I encourage you to try that on your own just for practice. But this is a solution, and if I were to graph the function y equals 1 over x squared, I get this, right? I have an asymptote at 0. What this is showing me is that the function that I'm using as my solution here is not defined on just a single interval. It's actually defined on a union of two intervals. So for this function, the domain of that function is negative infinity to 0, union 0 to infinity. In other words, all real numbers except for 0. When we want to use a function as a solution to a differential equation, we are not allowed to take functions whose domain consists of more than one disjoint interval like this. We only use functions that are defined on a single unbroken interval. And so for that reason, if I was going to call y equals 1 over x squared a solution to this differential equation, I have to restrict its domain to one of these two intervals, either 0 to infinity or negative infinity to 0. So an example here is if I decided to restrict my solution up there to the interval 0 to infinity, then the solution curve actually looks like this, not like this. Okay? Again, this is the distinction between just any function and that function as a solution to a differential equation. We cannot have any discontinuities in such a solution, so we restrict its domain to one interval on which it's defined. Okay. All right. Now, going a little bit deeper into the discussion of solutions to differential equations. Solutions can take different forms. Over here in the example that we just did, the two solutions that we verified as solutions to this differential equation are what we call explicit solutions. And an explicit solution is a solution where the dependent variable is isolated and it's given in terms of just the independent variable, y equals a function of x. Same thing here, y equals a function of x. It's not that uncommon that finding an explicit solution for a differential equation is very difficult or even impossible. And so for that reason, we sometimes have to be satisfied with finding a solution that comes in a different form, namely an implicit solution. Now this should be familiar from Calculus 1. You talk about implicit differentiation. So what do we mean when we say an implicit solution? Well, again, suppose we have a differential equation, some ODE, and remember this is kind of what I'm going to be using to represent a general differential equation. And let's suppose that we found a relation, so that's like an equation that represents a solution to this. G of xy equals 0. We call that an implicit solution if it's defined on some interval I, and there's some function that can be used as the y here that satisfies this differential equation. That's very kind of vague and I would say kind of unclear what we mean by that. But basically all I mean is this. Y we're still thinking of as a function of x, but we may not be able to isolate the y in this equation, giving y as an explicit function of x. And in cases like that, we're just satisfied with leaving it in this form. So let me give you an example to illustrate what I mean. So here's an ODE. It's given in differential form, and I want to show that it has the implicit solution, negative 2x squared y plus y squared equals 1. This is an implicit solution because the y, which is the function here, is not isolated. It's left kind of mixed up with the rest of this equation here. Now you could try and isolate it, but you're going to find that that's very, very difficult in this case. So we're not going to bother. We're just going to say that if this is a solution, we're satisfied leaving it in this form instead of isolating and solving for that y. But how do I verify that this is a solution to this? Well, it's tricky to find y and y prime to make substitutions in here. I can do it. It would involve implicit differentiation, which we're going to be doing anyways. I'm going to approach this in a slightly different way. If I were to take this equation here, this thing that represents our implicit solution, and differentiate it with respect to x, I should end up with an equation that can be put in this form, showing that this thing acts as a solution to this. So here's what I mean by that. Let's take this equation. I'm going to differentiate both sides with respect to x. So d dx negative 2x squared y plus y squared equals d dx of 1. Okay? Now this is going to be using implicit differentiation. So if you remember how that works, I have to use the product rule here. So I'm going to get negative 4xy minus 2x squared dy dx. That would be the product rule here with implicit differentiation, giving me that dy dx here. Differentiating this is going to give me plus 2y dy dx, and then over here the derivative of a constant will be just 0. Okay, now this doesn't resemble my differential equation up here yet, but that's because I haven't put this in differential form. So remember, to put it in differential form, we would multiply both sides by dx first. Notice also that I can divide everything by 2. I have a common factor of 2 here. In fact, I'm going to do one better and divide everything by -2, so I get a positive coefficient here. So I'm going to do a couple of things here. I'm actually going to multiply everything by -2 dx. Or sorry, -1/2 dx. That's to cancel the factor of 2 here. That's going to give me 2xy dx. So that's going to become positive now. That's going to become plus x squared dy. The dx will cancel that dx. Minus y dy equals 0. Okay? As a final step, I have a couple of terms with dy's in them. I'm going to factor that dy out. 2xy dx plus x squared minus y dy equals 0. And notice this thing right here is the original differential equation that we were dealing with. So I did this one kind of working backwards. Normally when you solve or when you're trying to verify, I should say, that a given equation, a given function, is a solution to a differential equation, you're starting with the ODE and plugging the solution into it. Here, I kind of worked backwards. I used implicit differentiation on the supposed solution and showed that the thing that popped out of that was the original differential equation. This works as well. Okay, moving down. So thinking again of this example that we did a couple of pages back, where I verified that 2 different functions were solutions to the same differential equation. I had mentioned back then that it kind of makes you wonder, how many solutions should we expect to find for a given differential equation? And it turns out that the overwhelming majority of differential equations, almost all of them that we look at in this class, that is, are going to have infinitely many solutions. That's generally the case, is that differential equations, if they have solutions, they will usually have infinitely many. But even though there are infinitely many, we can often describe all of them using some kind of representation, some kind of, well, we're going to talk about that here. So let's suppose, again, we have an nth order ODE, and it's here's that general way of representing that. What we look for in general when we're trying to find a solution to an nth order ODE is something that we call an n-parameter family of solutions. And it takes this form: some function of x, y, and then c1 through cn. These c's here are constants. I'm going to show you where they show up, but they're unknown constants. So because they're unknown, putting it in this form, you're kind of treating them as variables, but when we look at specific solutions, we think of those as constants. Okay, so those constants, those c's, are what we call parameters. And notice how there's n of them. That's why we call this an n-parameter family of solutions. We can substitute any real numbers we want into those parameters, and no matter what real numbers we choose to plug in for those, we should always get a valid solution to the differential equation that we're saying this is a solution to. So that because we can plug in any real numbers that we want into these, that's what generates an infinite family of solutions. Now, in practice and applications, we're usually not satisfied with an infinite family of solutions. Usually we want just one solution. And for that, we need a little extra information. We're going to talk about that in 1.2. But if we were to single out a specific solution from an infinite family, we call that a particular solution. This will be a really important term for a lot of the work that we do in this class. Let's look at another example. Here we're dealing with the same differential equation we dealt with a couple pages back. Y prime plus 4xy equals 8x cubed. And what I'm saying is this: y equals 2x squared minus 1 plus c e to the negative 2x squared, where that c is understood to be a constant. I'm saying that this is a family of solutions to this. Now, what that literally means is that for any real number c that I want to plug into this, that will create generate a solution to this. Compare that to what we looked at back here. So we had these two solutions here for the same differential equation, y equals 2x squared minus 1 and y equals 2x squared minus 1 plus e to the negative 2x squared. Comparing that to this, the first of those two solutions was choosing a value of 0 for c, causing that term to go away and giving me 2x squared minus 1. The second solution that we checked chose a value of 1 for c, giving me that plus e to the negative 2x squared there. But what this is saying is that no matter what constant we choose to put here, we always end up with another solution. So I can put in a 2 or a 3 or a 4 or anything like that. Okay, so I'm actually running out of time for this video. In the next video, I'm going to show that this is a family of solutions to that differential equation.